Hey everybody, this is Secret Squirrel's great buddy Morocco Mole, and this lesson is on section 9.3-1, the mean and standard deviation of your sample mean, your x-bar. Let's go ahead and begin. Okay, averages of several observations are less variable, they vary less from the population mean than individual observations, and you'll see an example of this towards the end of this short lesson here. Okay, averages are more normal for several observations than individual observations. Doesn't that make sense? Yes. Okay, mean and standard deviation of an SRS. Suppose that your sample mean, your x-bar, is the mean of an SRS of size n drawn from a large population with mean mu and standard deviation sigma. Okay, then the mean of the SRS of x-bar, there should be a bar on top of that, so just pretend like there's an x-bar on top of that, is this, you guys. Okay, your mean of your x's is going to be the same as your population mean. Okay, you had that on your homework just prior. And its standard deviation is this formula. Remember, that was in the last board problem right here. So standard deviation divided by the square root of n. Okay, this is when you do an SRS where n is something other than 1. Okay, all right, so the population mean is an unbiased estimator of the population, the sample mean is an unbiased estimator of the population mean, and the values of x are spread out for larger samples, and standard deviation decreases when n, or when the square root of n, increases. So if you increase your sample size for your SRS, your standard deviation will also decrease. Alrighty, to cut the standard deviation in half, you must take a sample time 4 times as large, because the square root of 4, okay, let's go back to this formula right here. Right here, the square root of 4 would be 2, so I would have to make this a 4 inside of there to make this a 1/2. So it would be the square root of 4, which would be 2, and it would become 1/2 right there. So to cut the standard deviation in half, you must take a sample size that's 4 times as large. That way you get the 2 in the denominator right there. All right. So women's height. So this is example 910 on pages 516 and 517. Okay, the height of young women vary approximately according to the normal distribution, 64.5. I suppose that's in inches, and 2.5 standard deviation. This is a population distribution with mean that's what it says right there. Okay, so if we choose one young woman at random, okay, this is one young woman, one, so we're just going to use this right here, our old school formula, then the heights we get in repeated choices follow this distribution. That is, the distribution of the population is also the distribution of observations chosen at random. We're going to use old school when we choose one woman. Okay, and I'll show you an example in just a second. So we can think of the population distribution as the distribution of probabilities, and just like in a sampling distribution. Are some of you guys going blah, 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 blah? Yes, you are. I can see you smiling. All right, so now measure the heights of an SRS of 10 young women. Okay, now the only thing that changes is this sample 2.5. The standard deviation changes, you guys. It's 2.5 divided by the square root of the number of our sample sizes. So since our SRS is size 10, then we do 2.5 divided by the square root of 10 is 0.79. Okay, and then we do the same calculations with the z-scores and stuff. Okay, write this down. The heights of individuals, women, vary widely, but the average height of 10 women is less variable. Okay, notice from each individual woman it was 2.5, the standard deviation, so it varied much less when we did a group of 10 women. It only varied by 0.79 on the standard deviation. Okay, so E, if you draw an SRS from a normal population with mean mu and standard deviation sigma, then the sample mean has the normal distribution. Okay, same thing, except I'm replacing the standard deviation with that new formula, standard deviation divided by the square root of n. And we do the same thing, you guys. Okay, so here we go. What's the probability that a randomly selected woman, singular woman, is taller than 66.5 inches? Okay, we're going to use that data we just got done with. Okay, notice it was normal, so I'm going to go ahead and plug it in. This is my x right here. This is the number we're focusing on, so that goes right here. the 64.5 is the mean, and the standard deviation is 2.5. So here we go, off to the racetracks, 0.80, okay, and it says taller, so I think I underlined that in the next part right here. Yep, I did, taller, so that means greater than, so we want this side, so the book gives this side, so we're going to do the 1 minus that action right there, and we get that. So I don't know if you can see that. I'll read it to you. It says down at the bottom, so the probability of choosing a woman taller than 66.5 inches is 0.2119. Okay? All right, so now let's try this with an SRS of 10 women. Okay, so we're going to do the same thing, except we just got to calculate the new standard deviation. Okay, so the only difference is our new standard deviation is the sigma, the old standard deviation, divided by the square root of n. Okay, and then we just do just like the last problem. So here we go. I get 0.79 from before. Okay, and then we're going to do x minus the mu divided by the sample standard deviation. So 66.5 minus 64.5 and divided by 0.79, you get 2.53. Okay, there's my fancy picture. I did that with my finger on my flat thing on this laptop right here. Okay, so the book gives me the 0.9943 for this side, so we do 1 minus that, and so it gets 0.0057. See how much less that is, you guys? It was 21% last time, and this time it's not even, it's a little bit over 0.5%. Okay, so it's very unlikely that we would choose 10 of them, and 10 of them would have an average that's bigger than 66.5. Okay, and this says here, averages of several observations are less variable than a single observation. A lot less. It went from 21% down to 0.5% right here. Okay, and if I increased it, it would be even lower if I increased the number of people. All right, so this figure right here, it shows you the difference between us, the two bell-shaped curves. There it is. There's the 10 observations right there. And then so I was looking for that little piece right there, and then the one observation. See how much this picture squares that away right there?